Hello, everyone. Thanks for coming. My name's Tom Waterson. I'm a lead on the Unreal Engine physics team, and I'm here with my colleague Marcus Boberg, who is a senior network programmer also on the Unreal Engine physics team. And in this talk, we're going to talk about physics-based character movement with networking. So I'm going to start out talking about physics-based movement and how we're starting to implement that in Unreal. And then Marcus is going to talk about the networking side of things and how we make this work smoothly in multiplayer. OK, so for my part, I'm going to start with a bit of motivation. So why do we want physics-based movement? What kind of things does it bring? And then I'm going to talk about what we've done and how it works and some of the challenges and the status and some of the things that you need to know if you want to implement this in your games. OK, so starting out on the motivation. So I'll start by describing a little bit about how the current default character works in Unreal. So the current default character is a kinematic infinite mass character, which is moved around via gameplay code. So you have a kinematic capsule, and then you use gameplay code to move it to where you want to go. It does collision via queries, overlap queries. So you decide where you want to go, you move it, you check for overlaps, you see if you're overlapping something, and then you use your movement code to pull it back and then potentially move again for the rest of the time step. And you can get some physics interactions this way. You can check that you're overlapping something. You can apply a force. You can even have a force applied to your character. But if you do, then your character movement code has to understand that force and know how to react to that, and you have to build that in. So in general, anytime you want to add anything new or any like custom physics or any new physics, then you have to code that yourself as part of your movement simulation. And in general, the movement is not two-way. It's usually just a one-way. I apply a force to you, you apply a force to me. And so we want to do better than that. So what we want is a dynamic character that's simulated as part of the physics world with real two-way interactions. And we want physics to matter. So things like the mass of your character, the character's momentum, the friction, all of those things should factor into how the character moves and it interacts with the rest of the world. We can also, so another goal is to try and simplify some of the gameplay code that we have to write in order to move our capsule around the world. So even something simple like I'm trying to move a character, but it's moving into a curved surface, and I have to go around that curved surface. Or if I'm moving into a corner and there's multiple collisions that I have to resolve. With the kinematic mover, these things have to be coded. These special cases have to be coded where I move here and then I move out of penetration. But we already have a physics solver. So the physics solver is set up to handle multiple collisions, multiple bodies, and resolve all of that kind of thing. And if we can use that physics collision instead of queries to do overlaps, then it can simplify a lot of the code that we have to write. And ultimately, we want to unlock real physics-based gameplay, so where physics matters as part of your game. So we've developed a new plugin. It's called Chaos Mover. So Chaos Mover extends the Mover plugin, which is another new system that we're developing at Unreal. If you're unfamiliar with Mover, there have been a couple of talks about this at previous Unreal Fests. But it's a new way of building extensible and modular character movement in Unreal. And it's really the future of movement in Unreal. And so what we've done with Chaos Mover is we've built a layer on top of that that allows you to have a dynamically simulated character as part of the Mover system, and one that integrates with network physics for physics-based multiplayer games. So kind of back onto the motivation, sorry. So what do we want to get out of physics-based movement? And at a most basic level, like we want to just be able to push into things and have that reaction be smooth and realistic. And as I said, we want things like mass and momentum to matter. So if I'm pushing something heavy, maybe I get slowed down. And if I'm pushing something lighter, I don't get slowed down so much. Maybe I can push multiple things at the same time. And also momentum. So if I run up to something and hit it, then I should be able to nudge something that's a little bit heavier. But if I start from standing and then I try and push it, then I can't overcome friction. So all of these things that you get kind of for free if you have a physics-based movement system. So we want that kind of dynamism, but we also want to give you control over how this works. So for the physics character, you can tune exactly how much strength your character can apply to the rest of the world. So as well as pushing things, we want the character to obviously be pushed. And so the physics character should be able to react to any external forces and collisions that are happening in your environment, and also obviously be like pushing back as well as getting pushed. And in general, we want the physics character to be able to interact with anything that's in the physics world, all of the different systems. So this one's an interesting one. So standing on a springy platform. So we want the character to be able to apply force down onto the platform to compress the spring, and we want the spring to apply a restoring force to push back up again. And this kind of thing is quite difficult to get stable if you're only interacting like through forces. So you really have to have something that's integrated into the physics solver where it can come to a stable equilibrium. So I mentioned using physics collision can simplify movement code. This is an example of this. So this is the kinematic mover character. And this is one of the edge cases that it doesn't quite handle at the moment. So sliding up a slope where there's like a slight lip on the wall that you're sliding against. And for the kinematic character, it's doing queries as it's going along. It detects that lip, it sees it as a ceiling, and it stops the character from moving. Now we could fix this, and we probably will fix this by doing more queries. But as I said, like if you use physics, then this kind of thing gets solved for free. So physics handles these multiple collisions. The character just slides along the edge and is able to resolve the collision correctly. So if you're using the new mover system, what you start with is a mover component. And the mover component is where you author all of your movement modes, your transitions, and your movement settings. And for the chaos mover, it's exactly the same. So we use the mover component as well. But we have a couple of additions that we have to enable. So on the mover component, you have the option to change the backend class of the mover. So the backend class is the thing that controls how the mover simulates. So it does things like how does it tick? How does the networking of input and state work? And so to enable the physics-based movement, you have to select the chaos mover backend on your mover component. The other thing that we have is we have extended the movement modes and the transitions to physics-based versions of those. So these are all based on the standard mover walking and falling and those kind of things. But we add additional physics parameters. So in this case, things like the force and torque limit that your character is allowed to apply when it's in a particular movement mode. So to move the character around, we've developed a custom constraint that's integrated with the chaos physics solver. And the custom constraint does two things. So the first thing is you give it a target for the character to move to, and the constraint will try and move the body to reach the target. So target position, target orientation. But crucially, it does that subject to a force and torque limit. So the constraint is only allowed to apply user-supplied force and torque in order to reach the target. And so if there's nothing else in the way, like if there's no other constraints that are preventing the character from reaching its target, then the movement will be followed exactly. So whatever you set as your movement target for your character, the character will achieve, and the physics character will move exactly the same as the kinematic character. But if it encounters another constraint, so say a collision constraint, if you're trying to walk into a wall, then the constraint solver will try and resolve those constraints together. And because the collision constraint can apply more force than your character movement constraint, it will in general win. And your movement constraint will try and get as close as it can to the target while respecting the constraint of the collision, so not interpenetrating walls and things like that. The second part of the constraint is the ground constraint, which holds the character up. So the user supplies a ground distance and a ground normal, and then the constraint says that the character has to be at least that distance from the ground plane. This is just showing some debug visualization of the ground query that's happening. We chose to use a query system for figuring out the collision with the ground instead of just using the capsule collision for a couple of different reasons. One, if you just use the collision directly, you don't have a lot of control over the ride of the character, particularly over uneven surfaces or going up and down steps. And so if we if we let the user say, this is what the distance is, this is what the normal is, there's a lot more control over how the character moves and behaves. And the second reason is just using collision, you can get cases where, say, things are overlapping when you're moving up steps, and maybe the collision pops the capsule out and it can introduce velocity. So we didn't want that for the character. We didn't want the character to be launched if it happens to be going over some uneven terrain. And so with the custom constraint, where we can push the character out of collision, but without introducing any additional velocity. So some teams just use a generic constraint in order to move a physics-based character around, say using a drive. That's perfectly fine. So you can do that, and that works well. One of the reasons for having a custom constraint, though, is it allows you to have tailored parameters which are exactly suited to character movement. So you don't have to have your designers figuring out what value of damping do I need to set on my drive constraint in order to get good behavior. And it also splits the constraint between the movement constraint and the holding the character up constraint. So holding the character up constraint is a one-way constraint rather than just an overall transform constraint where we're using a spring to hold the character where it is. So the constraint, and actually all of the movement code, so things like the mover input and the mover state, these are all integrated with the Chaos Visual Debugger. And so when you're recording things with the Chaos Visual Debugger, all of the data from the constraints, the input data from the mover and the output state from the mover, they're all recorded in the Chaos Visual Debugger, so you can scrub and inspect the parameters. And this is really useful for, say, if you're having client and server, where you want to check if things are in sync. Because the Visual Debugger records both client and server, and you can inspect the same tick, then you can do things like look at the input, say, was the input applied on exactly the same frame on the client and server? What was the output of the simulation? Did they diverge? Was there a desync? So this is really useful. So this is a very simplified diagram to kind of explain how the Chaos Mover update differs from the regular mover update. So with the regular mover, you produce an input. So this is things like your pad input, your button press, and that goes to the mover simulation update. That produces a target position and orientation for the character, and then you set that state on the character directly. And because it's using queries for overlaps, we may have to substep that process. So you try and move, you resolve the collision, and then you try and move for the rest of the step. But essentially, the mover says, this is where I want to go, and then you set the state on the character directly. With the Chaos Mover, it's slightly different. So it starts exactly the same. You produce the same input, and then you go to your mover simulation to produce a target. But now instead of setting that directly onto the character, you set a target constraint, a target for the constraint. That constraint is then solved as part of the physics update, and then you read out the actual state from the physics, which may or may not be where you set the target to be. Now onto some of the complications. So in order to work well in multiplayer, we require a somewhat deterministic physics simulation. And so what we want is if you set the same input on the client and on the server, you should get roughly the same output. So if you don't, if the simulation starts to diverge, it's not deterministic, and client and server disagree, then you end up with frequent corrections on the client, which can result in stuttering motion and just in general not a good feeling. And so we don't require exact determinism, but the closer to deterministic it is, the less corrections that you'll get. And so for physics to be deterministic, we require physics to run at a fixed time step. This is in general for physics simulations. They're only deterministic for a fixed time step. But Unreal is in general a variable tick update. So if you want to have a fixed physics tick, then you have to enable async physics. This is something that you can set in your project settings. There's a setting that says enable async physics. You have to check that. You can set the time step of the async physics tick. And what this will do is it will mean that physics runs at a fixed tick while the gameplay and the rest of the engine runs at a variable tick. So this is roughly how that works. So on the bottom, you have a variable tick game thread. So the updates are different sizes. And on the top in the yellow, you have the fixed physics tick. So when enough time has elapsed that we can launch a fixed physics tick that fits into the async physics time step, the game thread will launch a task to start a new async physics job, and that will run on its own thread. And so crucially, after it's launched this job, the game thread doesn't wait for the physics result. It can carry on ticking. And so when the physics result is ready, it will then get read back to the game thread. But we can't set that physics result directly onto the game, just the latest physics result, because if we set the physics result, then the game thread could keep ticking, and there could be like 1 or 2 ticks before you get the next physics result, and so on. So you could get a stuttered motion of your character. So we actually need to interpolate the result from the previous 2 physics ticks, and that enables us to have a smooth physics representation on the game thread. But one of the consequences of that is that the game thread representation is always slightly behind the physics thread representation. And at the most, it can be up to 2 times the async delta time away. So this has some consequences, which I'll talk about in a sec. Now, because we want the chaos mover update to work with physics, then it has to be updated on the async physics thread. So it's looking at the current physics state. It's setting the current physics state of the constraint. So we have to tick it in sync. And so we do this by registering a callback on the async physics update. So the chaos mover ticks on the async thread when the physics ticks. So this has some consequences. One of the most important consequences is because we're running the movement simulation logic on the async thread, that means that we can't directly access data that's on the game thread because the game thread is ticking at the same time. So we don't want the 2 threads to be clashing. So what we have to do is, when physics is about to tick, we produce input, so pad input. That all happens at the same time. But then also we have to gather all of the data that we need in order to run our simulation from the game thread, and then we push that up to the async physics thread. And then we use that data to update the chaos mover simulation, produce a target, that then goes to physics. And then when physics is done, we'll pull the state back down to the game thread, and that state will be interpolated, and then finally we'll get our resultant mover state. So one of the implications of running the physics tick and in async is that there can be some slight input latency. So I'll try and describe what's going on. It's quite difficult to see in this video, so we may have to kind of watch this back and pause it. But to describe what's going on, so the character is split in 2. On the left, there is a physics version of the character, and on the right, there is a kinematic version of the character. And they're both set to jump at exactly the same time. And I'm going to start this playing. And what you'll hopefully notice, the video will slow down in a sec. What you hopefully notice is that when the character on the right starts jumping a little bit sooner, as I said, it's very difficult to see. The character on the right will start jumping a little bit sooner than the character on the left. And the reason for this is, like, imagine you're on the game thread, you're producing an input, then you have to wait for the next physics tick in order to be able to consume that input, and then physics will run as gameplay is potentially ticking, and then we'll get the result back from physics. But even then, we have to wait for the interpolated result to catch up before we start to see the jumping motion. So the result of that is there's an additional latency between when I press the jump button and when I see the final result on the game thread, because the game thread is running slightly behind. Now, for most titles, this is not going to matter. It's a very small difference. And there are things that you can do to hide this latency, like through animation anticipation and things like this. But if your game is very twitchy and you require a very short input latency, then this may be a problem for that type of game. We are working on solutions for this, but this is the state of things at the moment. But if you put all of these things together, so if you have Chaos Mover to run physics-based movement, if you enable async physics so that we can have multiplayer work with physics, then you can start to get some really interesting things with multiplayer physics-based gameplay. And so you can have players interacting directly with each other. You can have players interacting indirectly through moving parts of the physics world, and everything works smoothly together. At this point, I should probably apologize for this demo. This was my own creation. This is the extent of my artistic ability in Unreal, but you but you get the idea. So this is just supposed to demonstrate. Here's an idea of the kind of thing that you can get if you enable physics-based motion and network physics, and everything's working together. So Chaos Mover is very much experimental right now, but it is available. So it will be available in the 5.7 release. So if you want to try it out, you can. In order to try it out, you'll have to enable the Chaos Mover plugin as well as the Mover plugin. And if you want to see some examples of a character setup, we have some examples in the Mover Examples plugin, and we have a chaos physics character set up with some example content, so you can play around with that. Also, if you're a UEFN user, when you enable physics on your project settings, you will actually be spawning in a physics-based character. So that's using all of the same technology in the UEFN physics character as this. And with that, I'm going to pass on to Marcus to talk about network physics.
Yes. So let's take a look at how network physics comes together behind the scenes. We will talk about how we synchronize time, and then the replication mode we use in what Tom showed, which is resimulation, what it solves, and then an issue that comes from it, and then how we approach that issue. And at the end, we'll look a little bit about sync and gameplay logic that affects physics. To start off, as Tom mentioned, we run a fixed delta time on the physics thread. That means we can link time to frame numbers. So instead of using time, we use the frame numbers instead. And when the client has connected to a server, it will send an RPC to the server saying, hey, I'm at frame 20. Server receives that. Server then sends back an RPC to the client saying, hey, when you told me you were at frame 20, I was at frame 100. And the server can have been running for 10 minutes or something, and then you join, so the server frame number can be whatever at that point. The client receives that back, and then the client calculates the frame offset between client and server. In this case, it takes 100 server frame minus client frame 20 equals 80. And now the client can translate between client frame and server frame. So it knows it can take the client can take its current frame plus frame offset and know that this is the corresponding frame on the server. And you can get this tick offset from the A-player controller or get network physics tick offset currently. The frame offset is always 0 on the server, which is useful. We'll get into that a little bit later. And we try to keep this frame offset static when after we first calculate it. But if the network conditions starts to differ, it takes longer for your messages to arrive to the server or shorter, then the server might tell the client, hey, you need to get in sync again. And the client will do that by scaling the time a little bit of the simulation. So it might tick a little bit faster or a little bit slower. Nothing you will see. It might be 1 frame over the next 100 physics frames. So it's doing this dynamically all the time to keep this frame offset in sync. But this means then that we have corresponding frames between client and server. If you look at the state of client frame 20, it should be equal to the state of server frame 100. And that brings us into timelines, because then we have corresponding timelines between client and server. And when you press forward, you start moving forward. You act then in your forward predicted timeline. I should say you press forward, start moving forward, you send that to the server, and then the server starts moving after you. But those happen on the corresponding frames between client and server. So those two timelines are already corresponding. And then we have another timeline, which is called interpolated timeline. And instead of trying to explain this further, I'll just show them to you. This is Chaos Visual Debugger. I have recorded with 2 clients and the server then. This is one player. So it's the autonomous proxy, and then the server, and then the simulated proxy, all shown at the same time in Chaos Visual Debugger. Currently, it's only showing the server player in red, and then I'll enable here on the right side the 2 clients, and they show up in blue. And then I will stop stepping the simulation, and the autonomous proxy will start moving because it's producing the inputs, sending those to the server. Server starts moving. The server sends the inputs to the sim proxy, and then the sim proxy starts moving. And here you have them. Forward predicted timeline for the autonomous proxy, server timeline for the server, interpolated timeline for the sim proxy. And think about throwing a ball at these. The ball will hit all 3 different entities here, autonomous proxy, server, sim proxy, at different places, or even miss the autonomous proxy, for example. So it's very hard to have physics interactions when your timelines are split up like this. But we already know that we have corresponding frames between client and server, and you can enable that in CVD, in Chaos Visual Debugger. That's what I'm going to do here. On the timeline sync, you flip to network tick. That will align your timelines, client server. And you can see here that the autonomous proxy and the server timeline align. They start moving on the same corresponding frame, but the simulated proxy is still behind. So we have aligned 2 of the timelines. And that brings us over to resimulation. A resimulation consists of a rewind. We go back in time, set physics to how it looked at that point in time, correct it based on data we see from the server, and then we step through the simulation up until our current timeline again. And to explain this and another issue coming up, we'll talk a little bit about inputs and input prediction. So at the top, we have the client autonomous proxy, your local player, then the server, and then the client simulated proxy, my player on someone else's computer. So the autonomous proxy at the top produces its input. It has the latest input, 12, but it takes time to send inputs to the server. So the server has, at this point in time, only received input 9, and the server sends it to sim proxies, and that also takes time. So the sim proxy has only received input 6. But we need to apply the inputs also. So we apply the inputs when we get them in the wrong, so to speak, timeline. The sim proxy will apply the input 6 on frame 12, which is wrong. And eventually that will lead to a desync. And when a desync happens, we do a rewind. We apply input number 6 on frame 6, where it should have been applied. And then we resimulate, predicting inputs based on the input we already received, and do that up until the current forward predicted time. And if we do that, it looks like this. Same thing, we have it set to network tick. I start stepping this forward. Autonomous proxy and server is in sync. Sim proxy starts moving. It detects, oh, I started moving on the wrong frame. And it's going to pop back, do a resimulation, which you can see to the bottom right. It's in resim. Step through the simulation, predict inputs, and then it goes out of resim soon here, and then it starts applying inputs that it receives in the still wrong timeline, but if the inputs are the same, it's going to stay in sync. And now we can start interacting with physics. I play it back again. Now you have the autonomous proxy, server, and sim proxy all aligned, and you can throw a ball at these. It will bounce off correct direction, etc. We have an issue with this, though. Some of you might have thought about it already. We predict inputs, and that means that when we stop moving, you will have predicted that you moved for a certain number of frames, and you have moved too far, and we need to do a rewind, stop the character, resimulate when having been stopped. But we render out the character in the for predicted timeline, so now we need to slide back, and that looks like this. So it doesn't look very good. And that can be solved, or one approach to solving it is introducing input decay. So the further into a resimulation, or the further into input prediction during a resimulation, we can decay the input more and more. So for example, if we want to decay by 20%, I'll actually take that in 2 slides, sorry. The input decay curve, first off, can be set via the Neprophysics settings data asset. And it's the one at the bottom currently, or rather by default, it's just three dots on the curve. And that works for many parts, but you might want to alter it if you have something more specific to balance. And the implementation of the input decay for the character just looks like this. It's a function on the input that gets called during a resim when we do prediction. And then it passes in the whatever value you have for the curve on the linear point during the resimulation. And in this case, it would, if you want to decay 20%, it would just multiply your move input vector by 0.8 to remove 20% of it. And when we balance that correctly, it can rather look something like this, which is much better. And now let's take a look at syncing gameplay logic. So anything that affects physics should run in sync between client and server, and it should handle resimulations. And that also means physics runs on the async physics thread, so you need to write logic on the physics thread. And I'll take 2 examples here, a kinematic moving platform, and then something we did with the pickaxe and weapons for the UEFM physics character. I'm not going to go through this, but this is logic to move a kinematic platform on the physics thread. If you look at the very top, this is in on pre-simulate internal. It's through an isim callback object, which runs on the physics thread only, or it ticks on the physics thread. And the key part here is the first line with colored functions. You get current frame, and then you add your frame offset. So we translate your current frame into the server frame, essentially. I call it corresponding frame here. But it is on the client, it's the server frame. And if you do this on the server, it's going to get the server's current frame plus 0, because frame offset is 0 on the server. So you still get the server frame. So if you base this logic in the if statement, you have if the corresponding frame is larger or equal to start frame of the kinematic mover, then it starts to start moving. And if the start frame is based on the server frame, this logic will produce the same input on the corresponding frame on the client as it does on the server, and isim callback objects, which is what the on-pre-simulate is integrated in will be called during a resimulation. So this logic also runs during resim and produces the correct logic during resimulations. You still need to network the start frame, end frame, start position, end position, etc. This logic doesn't handle the networking of it, but it handles the running in sync client server and during resim. That's essentially what this says. And this is how it looks. You have a kinematic platform in the background there that starts moving when I step forward here, and then the character will start moving, which you saw before, will also trigger a resim. And then if you look at the platform, it snaps back and resims in sync along with the character. I guess I can mention also that when the resim starts, it looks like it's desyncing. It's a Chaos Visual Debugger that shows the different parts of a resim. So the very, very first resim step, it shows the rewind correction, and that only happens on the client, so it doesn't sync the server part. So you see the red server part before it steps into the first resim step. So it looks like it might desync there at the very beginning. The next one is scheduled physics commands. And this logic is running on the game thread. So the decision to do something is done on the game thread. It's not really recommended to run your game on this, but it's a solution to make decisions on the game thread that affects physics and work in resimulation. What happens here, I'm also not going to go through the whole thing. What happens is that we add a force to an object. We, again, get the corresponding frame based on your current frame and the frame offset. And then we schedule a lambda function for the physics thread to run on a scheduled specific frame. And if that frame is the server frame calculated back to client frame or a server frame, depending on where you're at, then the physics thread will run that on the correct corresponding frame, client and server, and it will cache that lambda function in rewind history, replay it during a resim. And the lambda function is just to add a force to an object in this case. Same thing here. You need to yourself network the server frame in this case and the force vector and maybe the object that should receive the force. And this is how it looked without this implemented. The pickaxe works on the game thread, and it tries to add a force to the object on the game thread, which then gets overridden by the networking. So it looks stuttery. And this is with the solution. Much smoother. Upcoming work for network physics. We have a lot of work to do with optimizations, CPU and memory, and network bandwidth. And then new features. One large thing we are working on is a physics replication LOD system, so to speak. We don't only have resimulation as a replication mode, we also have predictive interpolation, which is running in Lego Fortnite, for example. But it runs in the interpolated timeline and can predict a little bit around that timeline. It's cheaper to run than resimulation, so we want to run it on things that are further away from us. And the issue there is when something that is far away comes closer to you, we need to bring it into your timeline, so that the forward-predicted timeline, I mean, so that you can interact with it in resimulation. And the solution for this is already in the engine. still experimental. It has issues. We're working on solving those issues of the transition. But that's coming up in the next release or the release after that, something like that. And then quality of life, mainly documentation. Some API changes, some new features, easier to make things. Currently, the network physics component is designed for a stream of inputs and states. But we also see a need for just event-based things, one-off events, for example. I can also say last week I put up a tutorial on how to actually implement network physics for a very simple custom pawn, just a ball rolling around by your inputs on the Unreal dev community. If you search for network physics pawn tutorial, you will find it. And it goes through how to set up client logic, or rather, sorry, game thread logic, physics thread logic, networking it, and everything. And that's it. Thank you very much for coming and listening.